Now let's look more closely at what happens when we toss an object in 2 dimensions in an environment where we have the gravitational force, where we have gravity. Now, for example, here what we have is an object that's shot at an angle relative to the horizontal. Now, as we have seen in previous examples, the minute it is off the shooting device, whatever that device is, the object is going to be subject to a unique force if we ignore air resistance. That unique force is going to be the gravitational force due to the Earth pulling on that object. Let's call it a ball, so Earth on ball. Since it's a unique force, that force is actually the net force acting on the ball, and being the net force, that means that that force is equal to ma. The acceleration is then just equal to 9.8 meters per second squared in the downward direction. So whenever an object is moving in air, subject only to one force, being the gravitational force, the only force that's acting on it being gravity, the gravitational pull of the Earth, then its acceleration is going to be 9.8 meters per second squared in the downward direction as represented by this arrow. Now, as long as the object is moving off the launching device and not subject to any other force but gravity, its acceleration is going to be 9.8 meters per second squared in the downward direction. So it's going to have that acceleration throughout the motion from the instant it leaves the launching device till the instant it touches ground. Remember again, we are ignoring air resistance, which means the whole time here we have a unique acceleration. It does not matter if you are climbing up at the topmost position or falling down, the object is going to have that unique acceleration, 9.8 meters per second squared. If we break the motion into segments, obviously before reaching the topmost position, that acceleration is going to slow down the object. At the topmost position, the acceleration is going to flip the direction of motion of the object from upwards to downwards. In the third component of the motion, then that acceleration is going to result in the object speeding up. Okay, let's look at the simulation first. That represents for us the acceleration. So if we play it, this is what we talked about. So I go back. So at no matter what position, our acceleration is going to be the 9.8 meters per second squared. Again, what I'm saying, no matter where we are, topmost position, climbing up, going down, it's 9.8 meters per second squared. Now,